This presentation is called, Hidden Helium Gas Prospect, a Possible Helium Incubator. My name is William Benzing and my degree is in geophysics. I call the name hidden because it lies on the backside of the Wichita Uplift in southwest Oklahoma. Unlike the front side of the Wichita Uplift, which is structurally complex and contains obvious structural traps, the backside sediment cover is thinner and lacks obvious structural features, which could be interpreted as hydrocarbon trapping. Besides the absence of geologic structures, the real reason I call it hidden is that the helium prospect lies below the top of granite. Normally, when the drill encounters the top of granite, it is assumed to be the economic basement and drilling is ceased. Geologically, the hidden helium prospect lies on the south or backside of the Wichita Uplift in southwest Oklahoma. The uplift is bounded on the north side by the deep Anadarko Basin and on the south by the shallow Hollis Basin. Questions and answers. Why should explorationists be interested in finding new helium reserves? There is a global shortage of helium, making helium very profitable. How is helium gas created in the earth? From the radioactive decay of uranium and thorium in granite. In a natural gas reservoir surrounded by radioactive granite, can the beta radiation, which are electrons, increase helium content? Quote, electron beam treatment can be used to concentrate helium in natural hydrocarbon mixtures. End quote. Chemical Engineering Journal Advances, 2023. Based on research work, you can increase the helium content of a natural gas reservoir by bombarding it with beta rays, which are emitted electrons from natural radioactive decay. This overhead illustrates how beta ray bombardment can significantly increase the helium content of a natural gas from 0.1% helium to 3.0% helium content. Given the amount of helium enrichment, I call that a helium gas incubator. What are the requirements for a natural gas reservoir to be rich in helium? Number 1, you need a granitic basement rock rich in uranium and thorium to generate helium and an organic source rock to generate methane. Number 2, you need a porous pathway for the natural gas and helium to travel upward. Number 3, you need a geologic structure to trap the natural gas and helium, and finally, number 4, you need an impervious caprock to halt the upward migration of gases. Necessary requirement number 1 states that you need a granitic basement rock rich in uranium and thorium to generate helium and an organic source rock to generate methane. This requirement is validated since the hidden helium prospect is located along the Wichita Mountain Front, which is a prolific natural gas producer and adjacent to the Panhandle gas field. The Panhandle field is one of the richest helium fields in the United States. Also, nearby well logs which penetrate granite indicate a high degree of radioactivity. This slide shows the location of the hidden helium prospect. It lies along the Wichita Uplift and adjacent to the helium-rich Panhandle gas field. This is a traditional buried mountain front model. The inclined granite wedge is generated by a low-angle thrust causing a steeply dipping front side and gently dipping backside. Steeply dipping folded and faulted structures on the front side become hydrocarbon reservoirs. The granite becomes the radioactive source of the helium and the organic-rich shales the source for methane. The amount of helium in most natural gas reservoirs is very small, usually less than 1/1000%. The presence of radioactive granite can raise the helium concentration. Concentrations 0.3% or higher are considered economic. This map shows the helium concentrations for the rich Panhandle and Hugoton helium fields ranging from 0.1% to 2%. The second requirement for a helium-rich natural gas reservoir is a migration path upward through the granite and overlying sediments. Given the small size and buoyancy of the helium atom, microporosity and microfractures in both granite and sediments provide the necessary upward path. Air versus helium. Helium is 7 times lighter than air. Helium atoms are 80% smaller than an air molecule and can move 3 times faster than air molecules. Helium atoms are very small, very fast and very slippery. Necessary requirement number 3 is a geologic structure to trap natural gas and helium. Based upon experimental rock mechanics and field data, a flat-lying recumbent fold, exhibiting structural closure, has been theorized to exist on the backside of the Wichita Uplift. The flat-lying, recumbent fold on the backside of a buried mountain front was theorized to exist after performing mechanical modeling experiments based on uplift and ductile shearing. Pre-existing surface folds, drawn on sliding glass plates in the bottom photograph, were uplifted by a low-angle upward thrust, shown in pink. The experiment produced the high-angle, frontal thrusts observed by deep drilling along the Wichita Uplift. Additionally, however, low-angle back thrusts were created on the backside of the uplift. After conducting the modeling experiments, a modified mountain front model was created. As shown in the new mountain front model, the old model was modified by the presence of a flat-lying, recumbent fold on the backside of the uplift. The flat-lying attitude of the fold blends in with the low-angle, monoclinal dip of the backside sediments. Seismically, this could cause the recumbent fold to be somewhat invisible and difficult to image. To trap hydrocarbons underneath a low-angle recumbent fold on the backside of a buried mountain front as shown previously, the uplifted folds must create structural closure when uplifted. If the pre-uplift folds were formed by transpressional forces, the folds will likely be somewhat asymmetrical. This mechanical model shows how to create structural closure underneath an asymmetrical wrench fold using uplift and ductile shearing. Ductile shearing can deform igneous, metamorphic and sedimentary rock. After the low-angle recumbent fold is formed, it looks very similar to a very large-scale recumbent fold in Greenland where the upper limb has been eroded off. This still shot of a flat-lying recumbent fold formed on the backside of a buried mountain front by uplift and ductile shearing clearly shows, with the aid of a level line, structural closure in the down-dip direction. Since ductile shearing can deform basement rock, as well as sedimentary rock, a subtle gas trap could be created underneath a thin, granite cap rock. The methane gas reservoir is, more or less, encased in radioactive granite which could then form a helium-rich gas reservoir. In case you doubt that granite cannot be folded, this photograph of folded granite was taken in an extensive mountain range in Chile called the Cordillera Darwin. As written below, the fold is defined by mafic dikes. The fourth necessary requirement for a helium trap is an impervious caprock to halt upward migration of natural gas and helium. The granite which seals the trap has been stretched out by ductile shearing along closely spaced shear planes separated by millimeters. To conserve volume, the granite is highly compressed. The shearing and crushing should reduce the microfracturing and microporosity, thereby making an effective seal for both methane and helium. This slide illustrates the gas permeability reduction in granite due to compression and shearing. The heat that is generated by internal friction during ductile shearing reduces the strength of the granite, closing microfractures and collapsing microporosity. Geologic cross-section B' is a north-south section through the hidden helium prospect on the backside of the Wichita Uplift. This is a dip section showing a flat-lying recumbent fold. The upper limb of the fold has been eroded by the Wichita unconformity and covered by Permian-age sediments. The granite basement and the early Paleozoic sediments have been deformed by uplift and ductile shearing to form a recumbent fold which exhibits structural closure. This structural interpretation is based upon the geomechanical modeling just shown. The model is of a flat-lying recumbent fold on the backside of a buried mountain front. The presence of deep structural closure is supported by the surface location of shallow Permian age, abandoned gas fields above the interpreted, subgranite closure. I was involved in drilling the Peoples 1 and 2 wells down dip. The number 1 well encountered highly fractured carbonates and TD'd in a possible granite wash. The hidden helium prospect can be tested by drilling a 6,000-foot exploratory well through the granite caprock into early Paleozoic sediments which may include granite wash. A residual Bouguer gravity map, in the area of the prospect, clearly defines the northwest to southeast strike of the high-density, Wichita uplift in lavender. Across the top of the uplift, section A' shows only slight color variation in lavender. A horizontal gradient map derived from the residual Bouguer map is shown below the residual map. The gradient data is used to highlight small changes in rock density. A dramatic change in color along the line A' is observed and signifies an area of lower density rock. This would be expected if low-density, gas-filled, porous sedimentary rock replaces high-density granite. Based on the gravity data, a lithology/density model is constructed on the left. The model shows an asymmetrical, high-density ridge with a low-density, sedimentary rock inclusion near the top of the ridge. This inclusion will cause a slight change in the residual Bouguer map and an amplified change in the horizontal gradient map. This interpretation supports the presence of gas-filled sedimentary rock below a thin granite veneer. Notice the unique, triangular shape of the low-density area at the top of the ridge along section A' in the horizontal gradient map. 2.5D structural modeling shows this is no accident but is due to the shape of the structural closure underneath a low-lying, recumbent fold. To get a better understanding of the closure shape underneath a flat-lying, recumbent fold, a series of 2D cross-sections were built of an asymmetrical wrench fold, before and after uplift. Using the uplifted cross-sections, a top-of-fold structure map is drawn and a closure structure map underneath the fold determined. The contoured structural map on the left was drawn based on the top of the yellow horizon structural model on the right. Because the uplifted wrench fault has a propeller shape due to the transpressional nature of the lateral stresses that created it, the uplifted fold changes shape along strike. The portion of the fold that is recumbent in the down-dip direction is stretched farther down-dip. This creates a structural low due to thinning. The portion of the fold that is recumbent up-dip is elevated into a structural high. On the structure map, the leading edge of the yellow horizon is mapped as the down-dip thrust fault due to its appearance on seismic data. The length of the recumbent fold is shown as the distance between the interpreted thrust fault and the blue line at the back of the fold. Notice how this distance varies along the fold and is maximum at the point of maximum recumbent fold length. Based upon modeling, it is at this location that maximum structural closure beneath the fold occurs and is designated by the red dot. The closure diminishes to zero around this location, with the bold black line showing the closure limit. Notice the outline of the closure is triangular in shape and points down dip. If the subgranite closure contains gas-filled, lower-density sediments, gravity data that indicates a lower-density material below granite should also have the same shape. Let's take another look at the gravity data over the hidden helium prospect. The triangular shape of the structural closure below the recumbent fold is reproduced on the gravity data along the Wichita uplift. In addition, an interpreted fault, called the Birch Fault, has been shown. Notice the spatial relationship between the kink in the fault strike and the closure outline are similar to the structural modeling shown earlier. Of significance is the observation that the horizontal gradient data has a triangular-shaped anomaly in the center of the subgranite, structural closure outline. Remember, the horizontal gradient data is used to detect small, lateral changes in rock density. In this case, lower density, gas-filled sediments below a thin granite caprock. As shown earlier, above the thin, granite caprock are abandoned Permian oil and gas fields. Several of these wells only penetrated a short distance into the caprock. As shown in this overhead, the subgranite, closure outline, which is the same as the prospect outline, is surrounded by the abandoned Permian gas fields. Should the hidden helium prospect be productive, much of the surface, gas transmission infrastructure is still present to help deliver the gas to market. Although the prospect outline is a triangle on a map, the actual reservoir shape, based on gravity and structural modeling, is displayed on the left. For simplicity in calculating reservoir volume, the reservoir is given the shape of a rectangular pyramid as shown on the right. The subgranite, sediment reservoir is assumed to be water-driven, with an average porosity of 12%, a gas saturation of 80% and a recovery factor of 70%. Assuming the gas is 100% methane, the maximum recoverable gas is 430 Bcf. Assuming the gas is 67% methane, 30% nitrogen and 3% helium, the maximum recoverable helium is 13 Bcf. To test this gas prospect, it will likely require a 6,000-foot test hole, possibly drilling 1,000 to 3,000 feet of granite. I am not an oil and gas operator, nor do I hold any oil or gas leases over this prospect. Finally, I would be glad to work with an interested operator as a technical consultant. If you have any questions, please contact me at cancerout@ymail.com. Thank you.